All right, polynomials. Now, there is a lot on this page because polynomials is a huge, huge topic. Lots of vocabulary, lots of things to call out. So this guy might take a minute, but it will be to your benefit, I promise. All right, so roots. Another word for roots would be zeros, x-intercepts, and solutions would also still be asking for all the same things. Now, these are a number, like the number where it crosses the x-axis. So like in this case, this would be a solution root or a 0 at that positive 4. So then that would be your root. So I'm going to put up here that our example is positive 4 from down here. Now, factors are not a number. They are a binomial with parentheses. So it's going to be x plus or minus a number, and it might be a number in front of the x as well, but x, theoretically, a two-term binomial. So in this case, like since our example was 4, then I would have x is equal to 4. That's my root. To turn it into a factor, I need to get it set equal to 0. So I'm going to subtract 4 from both sides. And then so my factor would be x minus 4. Just a throwback, because I'm going to do a couple of these on this page. If the root or the 0 was, let's say, 2/3, which is not the one I'm doing at the bottom. Oh, it is, because I always use the same one. So let's do 4/3. So if it was 4/3, then we would do x equals 4/3. You cannot have fractions. So we're going to multiply both sides by 3 to get out of the denominator. So undoing division. So I now end up with 3x equals 4. And then I'm going to try to get it equal to 0 again. So minus 4 on both sides. And so in this case, the factor would be 3x minus 4. So again, the factor would be in parentheses with two terms, the minus. The answer, roots, solutions, x-intercept is the single point at which it crosses the x-axis if it should be a real solution, real 0, real root. It's crossing the x-axis. Now, remember, we have real and we have imaginary. So real and imaginary. Imaginary, you have to make sure you remind yourself, very, very important, always in pairs. And I just misspelled always. Let's do that with one L. Always in pairs. So they are scared to sit alone. They always have to be in a set of 2. Now, you are going to look at your highest exponent to look at your possible roots, zeros, solutions, x-intercepts. So there's going to be 4 possible. Now, the different combinations of that 4, you could go look in your Desmos and see how many times it crosses the x-axis, but know there's 4 total. So since imaginary has to be in pairs, I can do 4 real with 0 imaginary. I can do 2 real with 2 imaginary. And then I can do 4 imaginary with 0 real. But I can't use a 3 or a 1 for imaginary. So I can't, because it's an even number, that means I can't have 1 real and then 3 imaginary, because that's an odd number. That would be one guy loner off. So every imaginary has to be an even number. So 4, 2, 0. So if you took that number and you counted down all the evens, so 4, 2, and 0 would be all of them. And then whatever would make up, because reals can sit by themselves. So that could be a 3 or a 5, depending on this number. But 4 plus 0 is 4, 2 plus 2 is 4, and 4 plus 0 again is 4. So that's how you could set up this possible sets. Now we're looking at a 5. So I can definitely have 5 real. Now we have to pay attention because that 5 is odd. I can have 4 imaginary. So, well, we'll work our way down. So 4 real would leave me with 1 imaginary. That won't work. 3 real would leave me with 2 imaginary, which would work. 3 real, 2 imaginary, and that's because 3 plus 2 equals 5. So we're trying to come up with combinations that keep imaginary in sets of 2 to equal 5. So then if I did 2 real, that would leave me with 3 imaginary with an odd number, so no good. And then if I did 1 real, that would leave me with 4 imaginary. That 4 is an even number, so that's perfect. And then my last choice would be 0 real, 5 imaginary. 5 is odd, so that won't work. So again, imaginaries have to travel in pairs, and these are the possible combinations of solutions. You can go put that in Desmos, like I said, and go see how many times it crosses the x-axis to find out how many actual real you have. But knowing it's a quartic or to the fourth power polynomial, there has to be 4 solutions, zeros or x-intercepts. Same for 5. If it only crosses the x-axis 3 times, so that means I know there's 2 imaginaries. But when I graph this, it is going to either cross 1 with 4 imaginary, cross the x-axis 3 times, which means I know there's 2 imaginary, or it's going to cross the x-axis all 5 times. So the ones with the 3s and 1s for imaginary are not even, and they're not pairs, so that won't work. Now I'm going to scooch over here to this graph. So we're going to discuss, this is something I remember lots of people calling out to be a little more difficult than we had hoped. So above the x-axis, this is our positive domains. So positive. So this is when the graph is positive versus going below the x-axis. Wow, that definitely says y. What is that ugliness? Sorry. So x-axis below it is going to be negative. So positive and negative. Increase versus decrease is the direction of the line as I look from left to right. So this is going to be my increase because it is going up. So if you think about like back to math 1, if I could close this off and that was all I was looking at, that's a positive line. And then if I look at this side, if all I was looking at, that's a negative line. So that's going to be my decrease. So that's my decrease side because it's going down from left to right. So decrease. So if we were looking, and always look at, so domains, it's always going to be looking at your x-axis. It's going to be very, very easy for you to start looking at the y, but you only want to look at the x-axis. So x-axis only, x-axis only for this whole conversation over here. All of this is x-axis only. So with that said, if I wanted to know where it was positive and increasing. So positive and increasing. So that means I want it to be going up and I want it to be in the orange. So that's 1, 2, 3. So this is -4. So that's where it starts in the orange as it's going up. Then it gets to 0 here and then it starts to go down. So positive and increasing would be from -4 to 0. And I did color this dot in because that's our turn point. But remember, it's our x-axis is only. So if I wanted to do decreasing and positive, so decreasing and positive, then it's going to start at 0 and it becomes negative at +4. So let's say decreasing and negative. So decreasing and negative. So that means it's got to be in the blue. This side is increasing in the negative before it goes into positive. Then our positive decrease, then it starts at 4 and then it goes on to infinity. So +4 to positive infinity because this side is our positive infinity. So again, your x values, x-axis only, x-axis only x-axis. That's the big misconception is you guys grab y values because you see it touch up here at the 1, 2, 3, 4, 5, 6, 7. A lot of you will put 7. It has nothing to do with that. It's all x values. The positive and negative does have to do with the positive y's, negative y's, but you're counting it in domains. So how much of this graph is positive would be from -4 to +4. So positive graph would be -4 to +4. Your negative graph, let's see if I can change color so I don't run all over the place. Negative graph would be from -infinity to -4 because then it goes into the positive, and then from +4 to positive infinity, and it's just coincidental that those numbers are both 4s. But the idea is that it crosses the x-axis and goes into the negative there. Now, this guy's a mess and a little bit of a sketch. So let's try to give us some numbers here so you can really talk about what's happening and where. This is, again, more discussion on our increase and decrease. So we have this is going down, this is going up. Beautiful. And then we're going to come back to end behavior. So reading from left to right, this is going to be an increase. So I'm just going to put IN. And then I have a decrease. Call it DEC, late December. Again, so this is going to be a turn point. a turn point, then I have an increase, turn point, decrease, turn point, and then ending on an increase. Now, so if we are looking at our increases, that goes from this is negative infinity, this is positive infinity, because we're only concerned about our x-axis. So it's going to start from negative infinity and go until 1, 2, 3, negative 4. Then it's going to decrease, and it's going to start at negative 4, going down until it hits negative 1. Then it's going to increase again from that negative 1 all the way up to that positive 1. And then it's going to decrease from that positive 1, 2, 3 to 3. And then increase again, because I'm going 1, 2, 3, from 3 to positive infinity. So you're literally tracking just going up, down, up, down, up. So increases your up and decreases your down, going from left to right reading. Okay. Now, different conversation in behavior. So in behavior, this is not, don't think as much about increase and decrease. Don't want to get you confused, but the in behavior is looking at how it ends and how the other starting end, if you want to think about the way looking at increase and decrease, the direction that it's going in. So x approaches positive infinity, which is positive infinity, and x approaches negative infinity. Positive is the left side, negative is the right side. So as I look from the origin to the right, what direction is this graph going in? And it is going into positive infinity because that's up here at the top. Then when I look to the left, I marked these wrong backwards. I hope I didn't say it backwards. I'm sorry, guys. So as I look to the positive infinity, that's looking to the right from 0, and looking at negative is to the left. I hope I said it different. So positive infinity is the right, negative infinity is to the left. As I look to the right from the origin, the graph is going up. That's why this is a positive infinity. As I look to the left, the graph is going down. So that's going to be our negative infinity. Now, knowing just that, there's some things we can talk about. We can talk about the leading coefficient of this, like if it was written as an equation, and we can talk about the exponent. So the largest exponent. So the first term, so looking at like these guys, like 2x to the 4th and negative x to the 5th, without seeing an equation at all, knowing just this right here, I know about the leading coefficient and the exponent. So leading coefficient, I guess I'll write that out this time. I was trying to save space. Coefficient, which I will notate as LC for anywhere else. So leading coefficient, exponent. The leading coefficient controls the right side. So leading coefficient controls the right side. And in this case, it's going up right here. So it's going to be a positive. So we know that the leading coefficient is positive. So leading coefficient, you're trying to decide, is it positive or is it negative? Then the exponent is controlled by the action of the second one in relation to the first. So at left, so the action of left in relation to the action of right. So calling this first, this second. So if it's opposite, these are opposite, so positive and negative, then we know that the exponent is odd. So it could be a 1, a 3, a 5, a 7. Because if they were even, then it should be the same. So they would both be positive, they would both be negative. But in this case, they're opposite, so we know that it's odd, which is interesting because it's 1, 2, 3, 4, 5 directionals. Like, so increase, decrease, increase, decrease, increase, which means it's a really darn good chance that that exponent is a 5. So the positive number, we'll just call it x, and we'll put a positive in front of it. We can pretend like it's a 1 for that matter, but it's positive x to the 5th would definitely be a good guess at the start of this polynomial when you're looking. So this guy is a negative, so the right-hand side was going to be going down. So that means as I look to the right, y is going to go down, so negative infinity, because the right is the leading coefficient. As I look to the left, the exponent decides it's odd, so it's going to be opposite, then our y value is going to go up. Look at the one above it. if I look at my leading coefficient, that decides my right. So x approaches positive infinity because that's the right-hand side of the graph. It is positive, so y is going to be positive. Our exponent controls the left side of the graph in relation to the right. So as I look towards negative infinity on the x-axis or to the left, y, because this is even, means the same. So since this is positive, this will also be positive. So that's your same. All right, moving right along. Multiplicity. So that's how many times it happens. So even, if it's an even multiplicity like 2 or 4, and then go all the way down the line, mostly we see 2 and 4. This is going to be a bounce. If it's odd, which we normally see it as like a 1, every now and again a 3, but remember that's 5, 7, all the way down the line, this is going to cross through. So think like linear equation is a cross through. Think like a quadratic is a bounce. So if I was to think about, see if I can make it match the one that I might give you guys later. So 4, so it bounced, right? It's going to go up. And then we'll say it goes down. Try to make it a curve. Go through 1. And then just for fun, let's make it look something similar to maybe what a 4th power. So 1, 2, 3, 4. Let's go right here. So it drags a little, like it's not with my markers and drawing it by hand is a little tough, but it drags a little, like it hangs out, like it's not a quick bounce. So a quick bounce would be a 2, a drag would be a 4, a cross through very quickly is going to be a 1. And then you've seen a cubic function, how it touches the x-axis and kind of does a snake thing, but it does cross through. That, again, it kind of lags. So the bigger the number, it lags in its place, but it still makes that cross-through action or bounce. So this is in 1, 2, 3, 4, -4 at a bounce, which means it's going to be a multiplicity of 2, which means we could write x minus 4, x plus 4, because the opposite squared would be the factor. So this would be the factor. This would be our root or solution. Where we're at -1, it crossed through, so it's going to be a multiplicity of 1, which means it's going to be x plus 1 with no exponent, because that's a cross through. And then over here, we're over at 5, that positive 5. We said it had a flat line, but it's still a bounce, so it's like a drag, but a bounce. So we'll call it multiplicity of 4. So that means it's going to be x minus 5 to the 4th power if you were writing this equation in factored form. So in factored form, that would be the factors you could use. Now, you could also multiply these out and keep going through if you had a little more information, but we just sort of sketched. Now, writing the polynomials, so writing -3 multiplicity of 2, which means it happens 2 times. So we're going to write it all the way out so you see what happens. So x is going to equal to -3 and x is going to equal to a -3. Now, that 2/3 that I told you about, multiplicity of 1 means it happens 1 time. Now, from here, we're going to solve it to get it equal to 0. So we're going to add 3. That's going to be x plus 3 is one of our factors. This is going to give us the same thing. So we're going to write it twice because it happens 2 times because it's a multiplicity of 2. Now, these are the ones you guys like to get excited and just throw in a fraction. No fractions in factors. So I now with 3x equals 2. Move that 2. So my factor is going to be 3x minus 2. And so these are my 3 factors. So these are the 3 factors, whereas above we have listed the roots, the solutions, or the x-intercepts. So these are the roots, solutions, or x-intercepts, and these are our factors. Now, to write the polynomial, you are going to multiply these together. You can do box method, you could do FOIL, you can do distributive property, whatever works for you. So first times first would be x squared. First times outer would be 3x, outer, inner, it's going to be 3x, and then last would be 9. So I end up with x squared plus 6x plus 9, and we've taken care of this factor and this factor. I do check on my paper, especially on tests, to make sure I don't forget one or leave one off. So 3x minus 2 is the next one we're going to multiply by. This one I'll do by FOIL or distributive property. So 3x times x squared is going to be 3x to the 3rd power. There are 3 polynomial, a multiplicity, so 1, 2, 3. So when we're done with this, if we do it right, it should be a cubic function because there's 1, 2, 3 multiplicities. So x to the third power. And then 3x times 6x is going to be 18x squared. 3x times 9 is going to be 27x. I'm going to switch colors so we can just stay tracking. So negative 2 times x squared, and I'm going to stack them. So it's going to be negative 2x squared. Negative 2 times 6x is going to be 12x, and negative 12x. And then negative 2 times 9 is a negative 18. Clean up and combine like terms, and you should end up with 3x cubed plus 16x squared plus, because 27 minus 12 is going to give me 15x minus 18. So minus 18. So great job. So that is your polynomial with those multiplicities as your roots. Just one call out real quick before I call it quits on this page. This will always be your constant, which is your y-intercept. So when you were trying to match a graph, it may be helpful if you're matching graphs to know this is your y-intercept. These are where it crosses the x-axis. And then we know that our third means at the end, it's an odd degree. So they're going to be opposite, and it's it's positive in the front. So it would look like this as far as end behavior is concerned. Whatever happens in the middle doesn't matter, but it's going to be going up on the right hand side and down on the left hand side. These guys over here are just for a brain break. I turned mine into a dragon on my first copy, my nice neat first copy. So hopefully you come up with something creative and fun to draw on there. All right, guys, awesome job.